So we're in the very last section that we're going to cover in linear algebra this semester, which is section 5.3. 5.3 is about diagonalizing matrices, which is a really big deal. Diagonalization of matrices. When can you diagonalize matrices? What's the procedure for doing that? But before we really want to get into this section, we want to look at a preliminary result. This result actually showed up in 5.1, but we didn't look at it because it really wasn't useful at all for 5.1, but it is in the background here. It's useful in 5.3. Really important result. I maybe could just state it and not prove it, but I thought, okay, well, let's do the proof because the proof is so elegant. So what does it say? Theorem. If V1 through VR are eigenvectors having distinct eigenvalues lambda 1 through lambda r for an n by n matrix, then that set of vectors is linearly independent, that set of eigenvectors. So basically it's saying eigenvectors that have distinct eigenvalues are linearly independent. Yeah, it's pretty easily stated. Eigenvectors that have distinct eigenvalues are linearly independent from each other. So how do you prove this? Well, you can get really fancy and you can do something called induction if you want to do it directly. But this is not meant to be a really technical proof class, so we're not going to get fancy. So we're going to just do proof by contradiction here. I think everyone can follow the logic of this proof. So we're going to assume what's called the antecedent. That's the part right after the F and before the then. Before the then it says, okay, so we're going to suppose V1 through VR are eigenvectors. And they have distinct eigenvalues, lambda 1 through lambda r for an n by n matrix, eh? So if we're trying to prove that a set of vectors is linearly independent, using contradiction, we're going to assume to the contrary that they're linearly dependent. Assume to the contrary that V1 through VR is instead linearly dependent. So basically our strategy is pretend, no, they're not linearly independent. Let's pretend they're linearly dependent. Then we're going to do some work. We're going to arrive at a contradiction. So because we arrive at our contradiction, then our assumption to the contrary must be false. So in fact, they must be linearly independent. That's our strategy. All right, so what does that mean? If you have a set of vectors that's linearly dependent, there must be a subset. Let's say we take away some of those vectors from this set. So I got a set of vectors. Let's say I take away some of those vectors. So I'm going to call this set the green set of vectors. Let's say I take away some of those vectors. Eventually I'll get to a point where some of those vectors are linearly independent. So there is a set of vectors, a subset. We'll call it what? V1, V2 through VP of that set of green vectors, V1, V2, VP, VP plus 1 through VR. That is linearly independent. Come on, man. So again, the reasoning is you have this set of vectors, V1 through VR, right? I call this the green set, V1 through VR. That's all the vectors. And what you can start doing, you can start taking away some of the vectors. You can take like VR away. And who knows, maybe that'll make your set linearly independent, right? And you can keep taking away vectors. So if you take enough vectors away, let's say VR all the way through VP plus 1, you take away those purple vectors, you're going to have a set of vectors I'm going to call the yellow vectors, right? These guys, V1 through VP, that'll be a linearly independent set. So here I got V1 through VP. That's my linearly independent set. Okay. So what does that mean? So v1 through vp are linearly independent. As soon as I add the p plus 1 vector, vp plus 1, it becomes linearly dependent. So that means then, let's call this equation 1. We're going to refer to this equation multiple times. That means vp plus 1 can be written in terms of the previous vector. So vp plus 1 is a linear combination of v1 through vp. So it's going to be c1 to v1 plus c2 v2 and so on and so forth. cp vp. And this is with the ci's, right? c1 through zp. These are called the ci's. These are just constants, right? They're real numbers. So vp plus 1 is a linear combination of v1 through vp. So what I'm going to do, I'm going to multiply that first equation by a on both sides. So multiplying equation 1 on both sides by a. What's that give? I'm going to hit it on the left side. And on the right side by a, it's going to give me what? A times, please write, thank you, vp plus 1. I'm not writing too well, equals. Now we're going to have a on the right side, a, that's not right, a times, then that yellow stuff, right? cv1 plus c2v. So on and so forth. So on and so forth, CP, VP. Close that off. And then you can basically use linearity properties for matrix vector multiplication. You're going to get something like, what? C1 AV1 plus C2 AV2 plus dot 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 CP AVP. Alien versus predator, right? AVP, alien versus predator. Okay, so we use linear properties, linearity properties, to carry that A through and to bring the C's up front. All right, so keep in mind that these VI's are all eigenvectors. So that means on the left here, I'm going to have what? Lambda P plus 1 VP plus 1, right? That's what AVP plus 1 is. It's lambda V plus 1. VP plus 1 because we're dealing with eigenvectors. And then here on the right side, right, we're going to have what? C1 lambda 1 V1 plus C2 lambda 2 V2 and so on and so forth. CP lambda P VP. I'm going to call this, this is going to be equation 2. Let's go. We're going to refer to this one again. So equation 1 is really important. We're going to refer to it again. Equation 2 we're going to refer to again. Let's start referring to equation 1 again. Let's multiply equation 1 by something. Multiplying equation 1 on both sides by, let's multiply by lambda p plus 1. The p plus 1 eigenvalue. What does that give? So I'm back here. I'm going to underline it in green. Underline it in green. That's equation 1. I multiply that by lambda p plus 1. What do I get? I get lambda p plus 1 vp plus 1 equals what? C1 lambda p plus 1 vp plus 1. Not writing at all. Please write. I don't know what this garbage is down here. Some kind of rubbish from somewhere else. I don't know what that rubbish is from. All right, keep multiplying. What were we doing? All right, we're multiplying lambda p plus 1 by equation 1. So we're going to have what? C2, lambda p plus 1, b2, and keep going. Dot, dot, dot. Cp, lambda p plus 1, vector vp. We're going to call this equation 3. Put a 3 out front here. Put a period after that equation. All right, so let's subtract equations 2 and 3. Subtracting equations 2 and 3 gives the following. Let's see. I don't know what this garbage is down here. Something left over from something else I was working on, I guess. All right, let's see. I'm going to use, what color? I'll use purple. I'll use blue. Okay, I'm going to take a... Come on. There we go. Lambda p plus 1, vp plus 1. I'm going to subtract the second minus the third. That's going to give me the 0 vector, right? Okay, then I'm going to take c1 lambda 1 v1 minus c1 lambda p plus 1 vp plus. That's not a p plus 1, that's a v1. Come on now. That should have been a v1 right there. That's a typo. All right, let's subtract those. c1 lambda 1 v1 minus c1 lambda p plus 1 v1. That's going to give me what? c1 lambda 1 minus lambda p plus 1 times v1. All right, then I'm going to subtract c2 lambda 2 v2 minus c2 lambda p plus 1 v2, and I'm going to get c2 lambda 2 minus lambda p plus 1 v2. And keep going down the line. Keep going. Cp lambda p vp minus Cp lambda p plus 1 vp. I'm going to get what? Oops, missed a plus sign there. Cp lambda p minus lambda p plus 1 vp. Right, please. Thank you. Now, remember that v1 through vp, these guys are linearly independent. If you go back and read that, where is that? Right? They're linearly independent. It's here in yellow, right? Yellow, right here. Highlight that. These guys are linearly independent. So because these guys are linearly independent, that means that their coefficients here for this homogeneous equation, they must all be 0, right? So since v1 through vp, that set of vectors, is linearly independent, then that means c1 lambda 1 minus lambda p plus 1 has to be 0. c2 lambda 2 minus lambda p plus 1, that has to be 0. And so on and so forth. Cp lambda p minus lambda p plus 1. All those coefficients must be 0. Now, what can you say about the lambda 1 minus lambda p plus 1, and the lambda 2 minus the lambda p plus 1, and the lambda p minus the lambda p plus 1? Those are all not 0, right? Because they're all distinct eigenvalues. Remember, lambda 1 through lambda r were all distinct. So lambda 1 minus lambda p plus 1, lambda 2 minus lambda p plus 1, lambda p minus lambda p plus 1, they cannot be equal. They can't be equal, so their difference cannot be 0 because the eigenvalues are not equal. So note, lambda 1 minus lambda p plus 1 is not 0. lambda 2 minus lambda p plus 1. That's not 0, right? If it were equal to 0, that would mean that lambda 1 and lambda p plus 1 would be equal. Lambda 2 and lambda p plus 1 would be equal, and they can't be because eigenvalues are all distinct here. And so on and so forth, lambda p minus lambda p plus 1 is not 0, since our eigenvalues are all distinct. Eigenvalues are all distinct. Okay, so what does that mean? If the lambda j's minus lambda p plus 1s are all distinct, what does that mean about C1 and C2 and so on and so forth? It's through CP. That means they have to be 0, right? In order for the whole expression to be 0. So it follows that. C1 equals C2, so on and so forth equals CP. These are all 0. So I'm going to go back now to equation 1, right? Equation 1. And I'm going to plug in place of these C1, C2 through CP. I'm going to plug in 0, right? We just solved for C1, C2, and CP, and we said they're all 0, so we can plug those back in. Okay, don't do that. There we go. Let's see if we can scroll a little bit. So thus, VP plus 1, right, is equal to, in place of C1, I'm going to put 0, V1, and then for C2, I'm going to put 0, and then V2, and so on and so forth. For CP, I'm going to put a 0, and then VP. That's just a bunch of 0 vectors added together, which is a 0 vector. But wait a second. Can VP plus 1 be the 0 vector? No, right? VP plus 1 is an eigenvector. It's one of those eigenvectors. And remember, eigenvectors are non-zero. So this is a contradiction. So thus VP plus 1 is the 0 vector, which is a contradiction. Since eigenvectors are non-zero eigenvectors. So here's the big contradiction we arrive at. We got a contradiction. So therefore, our assumption to the contrary must be false. So we assume that V1 through VR was linearly dependent. So therefore, in fact, they must be independent. Hence, V1 through VR must in fact be linearly independent. That is quite an elegant result right there. I'll stop there and we'll start actually doing some diagonalization results.